Today we're going to look at trapezoidal sums and how they work for the definite integral. We have used Riemann sums sort of as our on-ramp to, okay, we can estimate our area between a curve and the x-axis using rectangles. And one of the things that we noticed on that is that we were frequently either missing big chunks of area or we had too much of big chunks of area. So one of the ways we can improve that is instead of using a rectangle, we can use the average of the left and the right, which gives you what is called a trapezoidal sum. And what we're actually doing is this. Oops, forgot that I didn't have this on yet. Is that you have this curve here, and let's say we were just doing one subdivision. That's one subdivision of this. Instead of just using the left or just using the right or even using the midpoint, what we can do instead is connect those two and create a trapezoid. And we average these two heights together, right? Which kind of makes sense intuitively. It's like, oh, well, this one's too low, this one's too high, this one should be at least somewhat better if I average those two together. So that's called a trapezoidal sum. The reason that we don't do the problems in your book is your book is old enough, unfortunately, that it always does, much like it did with Riemann sums, it always does trapezoidal sums over a constant width interval every single time. And the College Board just doesn't do that. They're like, no, these can be any kind of a thing. Okay? So, for example, a car accelerates to pass another car on a highway. The table below shows the velocity of, I'm assuming, the first car at selected times. So it says, estimate the distance traveled by the car from t is equal to 0 to t is equal to 7 using a trapezoidal sum and the intervals in the table. All right, so you could, if you wanted to, do it like it says at the beginning of the lesson. Do a left sum, do a right sum, and average them. Being mathematicians, we're like, no, that takes too long. We're going to do this a faster way. So basically what we're going to do is instead of using either 81 or 95 as the velocity for this entire interval, what we'll do is we'll use the average of those two as the velocity for that interval. So the distance traveled is going to be approximately equal to, we'll take half of 81 plus 95, so we're averaging that out, times, that's a width of interval of length 2, plus half of 95 plus 103 on an time interval of 1, plus half of 103 plus 100 on a time interval of 2, plus half of 100 plus 81 on a time interval of 2. So you notice it's got a half in all of that. If we were to factor the half out and distribute, you would see that we have both a left and a right sum added together. Notice we've only, sorry, we'll just go ahead and calculate this. If this is a free response test, or free response question on the AP exam, just leave it like this. There's, again, I made a big deal of it a couple of times now. There's nothing to be gained by simplifying the numeric expression. All they care about is, can you get the numeric expression? And then if you say, hey, look, I can simplify, and don't do it right, well, that point that you gained gets lost. So here, let's see, the 2.5 will cancel, and that's 176 plus, Here they don't cancel, which is unfortunate. I need to take half of 198, which is 99. Plus, here the 2 and the 1/2 cancel, and I have 203. Here the 2 and the 1/2 cancel, and I have 181. So 1, 2, 3, 4, 575, 578, 579, 659. We'll hope that that's okay. So it's 659 feet. You may notice that in this, we only use the 81 once, but we use the 95 twice, because we're using it for both the left and the right. And then we use the 103 twice and the 100 twice, but we only use the 81 once because that only gets used in the right Riemann sum. It doesn't get used in the left Riemann sum. So that's how that works out. Page 2. So if a function is concave up, a trapezoidal approximation is greater than the true value. And I think you can see that pretty easily. We're getting extra in here. Conversely, if a function is concave down, and we do a trapezoidal sum, we're underestimating. And there's actually, we used to, in BC, learn a thing called Simpson's rule, which actually, it's a formula. And that's part of why College Board dumped it, is because it's really just a formula that people memorize. But what it does is it uses both you don't see it in the formula, you have to figure out how the formula was derived, but it actually uses the midpoint rule and a midpoint Riemann sum and a trapezoidal Riemann sum. And then I've forgotten exactly how it does it, but it counts one of them twice and the other one 3 times or something like that, and then divides by 5 because it's counted it 5 times. And it gives you really good approximations. What it actually ends up doing is it fits a quadratic to these 3 points. So it fits a parabola to those 3 points. And then finds the area underneath that parabola, is what it in essence does. You're like, okay, a parabola would fit that fairly well. And even this one, it's like, we can kind of think a parabola we could make a parabola come pretty close to this curve by going through these 3 points. So it's a rule, again, it's one that you may see at some point, but it's not one that we have to know for this class. So another way to improve Riemann sums, and we've already talked about this, but it's an important enough idea to where I think we need to go through it again, is to have more subintervals. Right, remember we talked about when you have just a very few subintervals, it's like a digital image that isn't super high resolution, it's very pixelated, right? It's very clunky looking. The more subdivisions you have, then the closer you are to the actual value. If we had enough of these, you wouldn't be able to tell that they were a bunch of little rectangles. You would be like, yeah, someone drew a curve. And it's like, no. Fact is, on your calculator, there are no curves on your calculator. It's just drawing a bunch of points that are small enough and close enough together to where it gives you the illusion of a curve. All right, so if we can find this limit, as n goes to infinity, of our Riemann sum, it's no longer an approximation, but it is the definite integral. Okay? Now, I don't remember if I've taught you guys this yet, and I apologize because I've added some into this unit. Have we talked about how to use a calculator to find a definite integral? Yes, okay. Then we will go on. So here, oil is being pumped into a tank over a 12-hour period. The tank contains 120 gallons of oil when T is equal to 0. So that's like an initial value. That's where we're starting. The rate at which water is flowing into the tank at various times is modeled by the differentiable function R of T. Values of R of T at selected values of time, T, are shown in the table below. Estimate the number of gallons in the tank at T is equal to 12 using a trapezoidal approximation with the 4 subintervals from the table. Okay, and this is one where I don't remember if this is an AP problem or one that's modeled right directly after one, but the one that was actually on the AP exam, there have been multiple ones like that. Students lost points because they did the trapezoidal approximation fine, but what they didn't do is find how much gallons are going to be in the tank, because they forgot to add the 120 to start with. So the number of gallons in the tank is going to be equal to 12 plus the integral, excuse me, it was 120, wasn't it? 120 plus the integral from 0 to x of R of t dt, where x is whatever that time is. So the number of gallons in the tank can be approximated by doing 120 plus a Riemann sum, or, as they asked us to do here, a trapezoidal sum. So it's half of 8.9 plus 6.8 times 3, plus a half of 6.8 plus 6.4 times 2, plus half of 6.4 plus 5.9 on an interval of width 4, plus half of 5.9 plus 5.7 on a time interval of 3 gallons. And although they don't always ask you to put the units on it, I try to put units on all the time. And then it tells us that a model for the rate at which oil is being pumped into the tank is given by the function g of t is equal to 3 plus 10 over 1 plus the natural log of t plus 2. You're like, holy cow, who came up with that thing? I don't know. Where g of t is measured in gallons per hour and t is measured in hours. Use this model to find the number of gallons of oil in the tank at times t is equal to 12. Well, so now we're just going to use what we wrote up here. This trapezoidal sum estimated the definite integral for us. And now they're saying, well, this is a model for the rate. Okay. So the number of gallons in the tank is going to be equal to 120 plus the integral from 0 to 12 of, because I'm super lazy, g of t dt. Why write all that out? Right? They've said that g of t is equivalent to this. So why not just write g of t? And at that point, it's just to grab your calculator and see what happens. Quit out of that. 120 plus math 9, the integral from 0 to 12. What did I do? I don't think I went over that far, but I must have hit it too hard. No, it's 3 plus. I don't want to do that. Yeah, I'll fix it in a second. 3 plus this fraction, 10 over 1 plus the natural log of t plus 2 all with respect to x. Oh, I know I keep telling you guys about the numWorks calculator. It's interesting on it. If you want to have a different variable, you can just keep pressing the X key and it'll keep going through variables that are likely variables. X, theta, t, n. It'll just cycle through those and you can go, oh, I can make it look just like this. I don't know that I want to hit, the key that many times, but it's an interesting thing. So it's 197.975. I have to tell you, now I'm interested in what did our trapezoidal approximation tell us that it was? 120 plus 0.5 parentheses 8.9 plus 6.8, close the parentheses, times 3 plus 0.5. And you can see I'm just killing time by doing this. 6.8 plus 6.4. And there are so many places I could go wrong. I might not type a decimal place. And then this is 6.4, 5.9. Oops, 5.9 plus 5.7 times 3. 198.75. All right. So, pretty good approximation. I think what they hoped on this is that if you didn't add on the 120, somewhere in your brain you would go, now hang on a minute. The oil is flowing into the tank at a positive rate. I should end up with more than 120 gallons. But again, it's easy to accidentally, to just kind of skim over that. I know you guys will be doing it digitally this year, but when it was on paper, what I told people to do is when you get to that, circle it so you don't forget that fact, or, write it down. Okay. I think the free response part is you're still going to be able to write things like that. But when you have multiple choice questions, I'm all about marking it up as you go through. Oh, this is an important idea. This means this, all that kind of stuff. And you are allowed scratch paper, so you can make yourself notes. It's just not quite as fast. Questions about this? Okay.